This is Mike Liu. He's on sabbatical here at the University of Hawaii.
I missed the introduction.
Yeah.
It was awesome.
So it's 15 minutes plus 5 for questions. After 12 minutes, I'll hold up a few fingers, and you can do whatever you want.
Maybe short on the questions. Okay. Good. All right. Okay. All right. Thanks for the great introduction, Andy. Okay. So my talk actually nicely complements Andy's talk. I'll be giving a bit of a status report and some new results on our state of using near-infrared spectroscopy, now bluer wavelengths than Andy talked about, to characterize planets directly imaged, that is young gas giant planets, and also their equal mass counterparts, the brown dwarfs, free-floating objects down to a few Jupiter masses, but without a star. Now, anybody who works in direct imaging knows the state of the field is in a great growth spurt, but I think there's also a bit of an intellectual crisis or roadblock coming ahead. I have a diagram to illustrate this, okay? And the diagram looks like this, all right? So this is the Peanuts cartoon that some of you may be familiar with. And here is the theorist. Lucy represents the theorist, and Lucy says, if you can image exoplanets, if you can directly image exoplanets, you will learn how they form and what they're made out of. All right, and the observer, the happy observer, like myself, I'm an observer, okay. Charlie Brown says, oh, I can figure out how to do that. Yeah, and all I've got to do is kick the planet football and all is going to be fine. And if you don't know the Peanuts, you should Google for the second panel, but I think most of us do. I'm not going to show you what happens next. All right, now, so broadly speaking, my research interests span two parallel tracks. One is through study of planets by direct imaging, okay, using high contrast adaptive optic systems. Here's a result from the Niki planet finding campaign that I led a few years ago, which shows the Beta Pictoris B planet, about a 10 Jupiter mass planet around a young A star. We can measure its fluxes, we can measure its colors, we can even measure its orbit. And then I also studied brown dwarfs, anything free floating below the hydrogen burning limit, all the way down to a few Jupiter masses. Here's a very interesting object we found a few years ago, PSO 318. It's about a 6 Jupiter mass, 12 million-year-old object, all by itself. In fact, it's coeval here. These two things are in the same moving group. And then myself and members of my group, we're from Hawaii, so we use the telescopes in Hawaii. This is the Keck telescope. So it has a high contrast adaptive optic system. You can take great images of faint dots next to bright stars. And then to find brown dwarfs, they're very faint and they're very rare on the sky, so we use wide field survey telescopes like the Pan-STARRS telescopes. These provide a multicolor, multi-epoch map of the whole sky. You can look for things that are very faint and nearby from their colors and their motions. And then, of course, we get spectra, right? So a few years ago, for instance, this is the first near-infrared spectrum of one of the 8799 planets taken by, at the time, my student, Brendan Bowler. He's here someplace, I think, or he was observing last night, so maybe he's not awake yet. But anyways, this is a near-infrared snippet. Spectra have gotten better, but systematics are still an issue with published imaged spectra. Spectra of imaged planets. And then brown dwarfs, of course, we collect very rich spectra because they have no bright star next to them. You can get a broad range of wavelengths and great spectral resolution and so forth. Okay, so today I'll be talking about sort of an empiricist view of what we can learn from spectra. All right, we've heard some really great talks about all the very high fidelity physical effects that go into generating the atmosphere of an object and thereby producing its spectrum. But if we step back simply from the naive observer standpoint, that is, we spend all this effort collecting a spectrum, what are the physical effects that we're tied to, that the spectrum is tied to, that we're trying to extract? And so just, in the broadest conceptual sense, you can think of this as some kind of Taylor expansion, right? So to first order, you might measure the brightness of an object. That's pretty straightforward, reflects how much energy comes out. But then you care about the high order things, the first order, the temperature, to second order, so to speak, the gravity, all kinds of interesting stuff to third order. So this is what the aim of carrying out so many of these observations is. And we do them in the near infrared because that's where they're easiest to detect and they're extremely bright. Now for the exoplanet case, we know that the number of exoplanets directly imaged is pretty small. It's about a dozen objects. Okay, so that's they're incredibly important, dozen objects, but it's fundamentally a limitation. And there's a way to view this limitation, which I'll show here. So for instance, this is the 51 Erie planet, recently discovered by the GPI team. We worked very hard for many years to survey many stars, to find a small number of planets, interpret them with state-of-the-art physics and so forth. But at the end of the day, fundamentally what you're studying perhaps is really just sort of one butterfly. You've collected one object, you've scrutinized it very carefully to the maximum of your ability to interpret the appearance of the butterfly, but it really is only one butterfly. Past that, you might do another survey, and you work very hard and you find a second butterfly, and then you work very hard a few years later, you find a third butterfly. Right? But the Taylor expansion, I told you, has many terms. Right? So it's a multi-dimensional space, and you can't map that with a small number of points. What you really need is a very large sampling of the parameter space, and this is what the brown dwarfs are a great complement. Okay? Although there are, say, a dozen directly imaged planets, there are 1,000 or more brown dwarfs known to date. All right? And so we can map out the full range of butterflies, their color, their sizes, where they came from, how they fly, so forth and so on. And physically what this means is that we want to understand how these effects alter the spectrum. So we want a broad enough set that we can, for instance, map as we turn the temperature knob empirically, what do we see in the near-infrared spectrum? Because we know that first principle predictions are still very challenging. And likewise, empirically, we can turn the knob and get gravity, and so forth and so on. Now I'm turning into Mike Line, but you get it. Okay? So the idea is that with a large enough sample, you can map the parameter space. So let's see what we've accomplished so far. Okay, so the zeroth order thing is luminosity. This is pretty straightforward. You measure magnitudes and colors for things. This is a color magnitude diagram. Right? This is the absolute H-band magnitude versus infrared J minus K color. These are stars up here. And the L and the T dwarfs are the ultra-cool objects down to the Y dwarfs. The dots are the field objects. They're free-floating. And then the special dots are directly imaged objects, I think below about 15 Jupiter masses or so. Okay, so they are indeed an overlapping population for the most part. And then there are a few deviants, which I'll get to later. This is by a review article by Brennan and KSPA, which covers the state of our observations from direct imaging. Okay, what about the next term in the series? Well, that's temperature. Okay, so one of the triumphs of the last 15 or 20 years or so in this field is the connection of the lowest mass, coolest stars to the highest mass gas giant planets. And this is a schematic of that grand unification, so to speak, that ties everything together as you move through the four coolest spectral types, the M, L, T, and Y dwarfs. And as Andy pointed out, the coolest object we know of to date is 250 Kelvin. That's only a factor of 2 in temperature, so to speak, from Jupiter. And each of these classes is empirically distinct. The spectra look qualitatively different. You wouldn't have to be an astronomer to recognize that an L dwarf looks different than a T dwarf. If you just hand it to anybody, you can see that the bumps and wiggles are very different. Now, it's worth remembering, because this is a school, and maybe not all of us are astronomers, that this is a temperature sequence. It's not a mass sequence, all right? Because these things have no internal energy generation, the mass and the temperatures are all mangled together. And so, for instance, if you want to think about this in terms of a mass sequence, low mass stars reside here. They include M dwarfs and also L dwarfs are low mass stars. Brown dwarfs down to the IAU mandated limit of 13 Jupiter masses cover the whole range of M, L, T, and Y dwarfs. And then planets, again, the 13 Jupiter mass limit, span the remaining classes. So a young, very hot 13 Jupiter mass object is as hot, if not hotter than, the lowest mass stars that we know about in the solar neighborhood. Okay, so this is what we measure empirically, spectral type, but how that couples to mass is a little bit tangled. Okay, so the first order temperature is pretty good. How about past that to second order? Well, it's been pretty clear over the last couple of years that things get more complicated. This is a series of objects, brown dwarfs, discovered in the solar neighborhood. They're all L dwarfs, so they're pretty similar spectral type, so they should be pretty similar temperature. And so you can see the spectra and the optical, where a lot of the classification done is fairly similar. But there's a broad diversity when you go into the near infrared. The black object represents an old object, so hundreds of objects have these sorts of spectra because most things that you find free-floating are old. But there's a rare population, a subset of the population that spans a broad range of colors and shapes and goes all the way up to this 5 Jupiter mass planet, to mass 1207. Okay, so the challenge in the last couple of years has been recognized is that we have a good system that works here. How do we make sense out of all of this? All right. We think this is gravity. We think this is things of different age and different sizes. Okay, and how does that impact the spectra? Well, it's pretty straightforward. If you have an object, a brown dwarf of the same temperature, in this case 1400 Kelvin, so it's a mid or late L dwarf, a 1400 Kelvin object with an age of only 10 million years, like directly imaged planet, will be 7 Jupiter masses, and it'll be have a radius of about 1.5 Jupiters. Whereas an old object at a gigayear at 1400 Kelvin would correspond to a 50 Jupiter mass object about 1 Jupiter in radius. So this object is far more massive, it's much smaller, so it'll have a much higher surface gravity, and that imprints itself on the spectra as a second order effect, so to speak. Okay, so what we've been doing the last few years is figuring out how to make sense of this. We need to classify things, right? We've got hundreds of things, and you want to be able to turn them into a small number of bins which describes what's going on. And so the spectra that I showed you, the big jumbo spectra, they're various shapes. Some are pointy, some are flat, they're different colors, and so forth and so on. And so we need a system that turns them into a small number of things, spectral types, and this thing that I'm going to talk about, gravity class. Now the way this is done is very straightforward. It's well established. You know, stellar spectroscopy in the 50s with Morgan and Keenan. They didn't know a whole lot of stuff that we know about stars now, but they were able to establish a classification system just by looking at the bumps and the wiggles. Okay, so for instance, these are photographic plate data for stars of different types, and you don't have to know anything about quantum physics to see that certain features come and go in strength. And so you can label objects. There's a system that comes out of this purely empirically, and then it turns out that system is tied to an underlying physical property. So again, well established for stars, and we just need to do this for brown dwarfs down to the planetary mass objects. So with Caitlin Allers a few years ago, we set out to do this. We collected all the butterflies, and we started sorting them. All right, so we collected a lot of spectra. We used the same instrument. We collected a broad wavelength, similar resolution, and we sort of laid out how they'd look. And here is some representation of that large collection of butterflies. And what we did was, just like Morgan and Keenan did in the 50s, was we looked for things that changed in certain ways. So for instance, at low spectral resolution, here's the near infrared, here's the H band, you can see it changes shape. The other bands are fairly similar, but for instance, it goes from this sort of triangular shark fin kind of shape to a flat top, okay? And you can also see it, this is low resolution R of 100, and then at R of 1,000, you can see that higher order features, in this case the potassium and sodium lines, also change strength dramatically, while the other features are relatively constant. So there are features in the spectra that we know change, and we have some guidance as to whether they correspond to temperature and gravity that I'll talk about later. Once you can use your eyeball, of course, then you can measure things with numbers, and that's what we did. We set out and defined a series of indices, and we identified some as temperature sensitive and some as gravity sensitive. So for instance, this is a water index. We're basically just measuring the shape of the depth of water absorption in a bandpass. And each of these dots represents a collection of objects in the sample, and then is plotted as a function of optical spectral type, as I mentioned, already predefined. So certain near-infrared features track well with optical spectral type. And certain gravity features track well with near-infrared spectral type. So you see, for instance, they have the same spectral type, but there's a huge dispersion. So we put things into bins. We put them into 3 bins to represent gravity. We called one very low gravity, one intermediate gravity, one field gravity. Not that creative, but you know that's astronomy for you. Okay, so there are 3 gravity bins, basically. And so there's a system. You measure a series of indices, it defines a type and a class. And then if you want to do it the old-fashioned way, you can also compare to a series of templates that we set up. Okay, and so this is now routinely used. Here's some things that have been recently discovered. Here's an 11 Jupiter mass free-floating object, and this is an object straddling the deuterium burning limit, so it's either 12 or 25 Jupiter masses. The dark object here is the dark points here are the spectrum. The red are our standards that we set up, and so you can see, for instance, this L7 very low gravity standard we set up is a good description for the discovery. If you want to use flux indices, you can do this as well. In this plot here, the red object now is the science target, and the bracketing blue ones are the higher and lower gravity objects. So this is an intermediate gravity object with a higher gravity and lower gravity object between it. Now, if you're a skeptic, you would say, all I did was I identified a bunch of bumps and wiggles. Some are very big, some are very small, and then I put a physical label on them. But how do you actually know that what you're measuring corresponds to the physical property you care about? Well, for bolometric luminosity, it's straightforward. We just iterate the spectrum. We don't have to worry about that. Okay, so let's talk about temperature. Does spectral type really map to temperature? And this is very well established now. The way you measure the temperature independently is you have the bolometric luminosity, and you know basically everything's the size of Jupiter, so you add it up, Stefan Boltzmann law to give you, use the Stefan Boltzmann law, luminosity radius to give you the temperature. And here's the spectral type, and here's the data. So indeed, here the swath represents the results. So indeed, spectral type tracks with temperature. For old objects, Young objects follow a slightly different relation, but it also tracks with temperature. Things break down here. We don't have to get into that. But yes, okay, spectral type seems to work well. What about this other thing? Gravity class. Does gravity class really map to surface gravity? It's hard to measure the surface gravity directly, so we need a proxy. All right, and our proxy is age. Brown dwarfs shrink over time. Okay, there's an early phase where they're big. There's a phase where they basically have constant radius. So if you can find young ones, the objects are shrinking. And so you should be able to track this essentially as a proxy for age. So we did this. We found brown dwarfs of a particular age, and we asked, how does the distribution of gravity classes change? Okay, so for instance, at 10 million years in one of these young star associations, everything is very low gravity, has the same gravity that's very low. As you transition to 20 and 50 million years old, there's a change. And when you get to 100 million years old, most things are in intermediate gravity, and only a few things are low gravity. The plots are different. The heights are different on these bars because these stellar associations have different numbers of objects. But the idea is simply that you see more intermediate gravity objects at the older ages, fewer or none at the very young ages. So indeed, these bumps and wiggles that we've labeled as gravity behave, roughly speaking, as you expect. Okay, now, a few loose ends. There's this gravity clock I talked about. It works pretty well, but it doesn't work exactly. If you look in AB Dor, these are all the brown dwarfs known in AB Dor, confirmed brown dwarfs, I should say, in AB Dor. There's a mix. And the mixing doesn't really make a lot of sense. You might expect there to be, say, hotter things are one gravity and lower things are another gravity, but that's not the way it is. Things are intermixed. And even more confusing, for instance, these two objects in the group of the same spectral type and age have different gravity classifications. And by coincidence, and there's only two objects, one is free-floating, one is a companion. So maybe something interesting is going on between things that were born bound to a star and things that were formed all by themselves. There's another loose end, another interesting thread, is that if you plot the velocities of things with low gravity, they're pretty low, as you expect. Things that are freshly born should have low velocities. They haven't had a lot of gravitational interactions with stars to speed up. But a small fraction of them are extremely high, 100 kilometers per second, which is completely unheard of for a young star. And so the question is whether there's something funny about the classification system, that we've somehow mixed in old stars here. I don't think that's the case, but it could be. Or perhaps there's a rare population of low-gravity, super young objects that are actually born with extremely high velocities because of some early dynamical interaction. And then the final loose thread is that it probably ties to these third-order effects that we all think are very interesting, like metallicity and abundances and so forth. If you look very carefully at the spectra of free-floating objects and companions, even in the same age, okay, all formed out of the same gas, there are subtle differences. It's a little hard to see. This object is a 14 Jupiter mass object in the upper SCO group and is compared to free-floating objects here. So black is the spectrum and blue is a series. Black is all the same spectrum. And blue is a series of things in the group. And so, for instance, even the best match here at one band shows small differences in the shape and the angles of others. They're pretty subtle. They're hard to pick out of the data. But they're in multiple objects. And I've just chosen one. Many of the objects discovered by companions in the same group, if you match them up to other objects, there are small discrepancies. It'd be very interesting to understand what the underlying physical cause of this is. We don't know. And there's also a hint, which I'll talk about more probably in the longer talk, but if you look at the color magnitude diagram for these objects, companions in blue, free-floating objects in red, they do appear to form distinct sequences, which may again be an indication that they have a different formation history. Okay, just to wrap it up, we know a lot of brown dwarfs now. We know a lot of young brown dwarfs. We have a reasonable sample of directly imaged planets. We have good near-infrared spectra, and we can develop a very effective classification system to separate them. The data show that, in fact, the classification system, which is purely empirically derived, does tie to the underlying properties you care about, temperature and gravity. So when you find something new and you classify it on the system, you know something about its physical properties. And a number of loose ends in the classification, basically which have been swept under the rug or perhaps I think not fully appreciated, may be a very interesting window to understand some of these higher order effects. Perhaps ones, for instance, do free-floating brown dwarfs and companions form in different ways, and is that formation difference reflected in their spectra, their colors, and their magnitudes? Thanks. I'm sorry, say again? Right. I mean, at a given, for given gravity at the location of the photosphere, right, the pressure is different, so that'll have an imprint on the particular molecule or the atomic species in the shape and the depth of the line. Sometimes there are individual line features, like I showed individual features of sodium, potassium. For something like water, which has absorbers all over the place, it alters the underlying shape of the continuum of the object. Yeah. Let's see. This one. The free-floating one is the lower gravity one, the fluffy one, as you say. And the companion is the higher gravity one, so the more compact one. I'm not quite sure which way to expect one way or another. Right. Right. This is at 100 million years. Okay, so these effects diminish over time. So, but something lasts very long spectroscopically. At 1 million years, the sky's the limit in terms of what these things could look like in terms of their gravities. But this is getting pretty old, and these things are, I think this one's about 20 Jupiter masses or something like that. So it's pretty long-lived. I don't know. I think there are a lot of other effects that could be going on that imprint themselves, and rotation or differences in composition, which affects differences in clouds, which alter the spectral features, which then get kind of shoved into these. We're forcing everything into two bins. So I think that may be an issue. But I think it's very actually. So one of the points is that with a much larger sample in AB Dor, which one of my students is working on, we can look at this much more systematically. So we've only got about 7 or 10 now in AB Dor, but when we've got 100, not 100, we'll never have 100. But when we have many dozens, it'll perhaps be more clear what's going on.
A question about the high velocity, low gravity object.
Yeah.
You can imagine it might be easier potentially to accelerate low mass objects to high velocities compared to stars. Is that an effect people see, that like M stars have higher velocities than like A stars because of mass differences?
Well, there is it's for old stars. There is a difference in their velocity dispersions in the disk. M stars have higher velocity dispersions than A stars. That's also a reflection, of course, that A stars don't live as long as M stars. So A stars, right, they go off the main sequence faster. So they haven't as much time to have as many dynamical interactions. But even then, that's at hundreds to billions of years old. And these are things which are all 100 million years or less. So it's probably not due to gravitational interactions after the fact. If it was due to gravitational interaction, it must have been in the beginning when they were all born together and something happened, either in the disk or in the birth cluster.
Would you ever see that for, I don't know, K or M stars?
Runaway young stars is extremely uncommon. I'm sure there's some exotica, but nothing springs to mind right away. Yeah, right. Isn't that annoying? Yeah, right. So if you're a purist, right? If you're a purist, okay, I don't need to show it. But if you're a purist, right, your spectral type is based on the part of the spectrum you use to classify the object. So there's a system in the optical based on various features, bumps and wiggles in the optical, and there's a system in the infrared. And I think the point of my slide was to show that although the system in the optical, let's see if I get to it. It's not really necessary. The point of the slide is that the system in the optical is pretty well established, but the system in the infrared has been kind of the wild, wild west for the last couple of years. And that's actually kind of why we were motivated to dive into the, Jesus, sorry. It's kind of why we were motivated to dive into this thing in the first place, is that there's a well-established system down here. But if you were to take 3 things in the optical, actually I've got labels here. For instance, this is L6, and this is L6, and this is L6. These are all optical labels, right? So but their infrared spectrum are completely different. So the system that works in the optical doesn't work in the near infrared, and it's probably because we need the second dimension, which we label as gravity classification. I'm not naming names. Okay.
All right, let's thank Mike again.
Good.